Greetings. I'm going to start today's lecture asking the question, what is a vector? Basically, a vector is something that has a size, which we also often call a magnitude, and a direction. And it's represented, let's say, think of a good name for a vector. Vector R, something we're going to be using for position vectors shortly. R has both a size, which is just given by R like that, or the full vector that includes both the size and direction is going to have this little half arrow on top of it. That's just the symbol that's often used for a vector that we will use. Quick way to reflect what the magnitude of R is to put absolute value signs around the vector and say that that's equal to just R, which is just the size of the vector. Okay, so a vector has both a size and a direction. And it can also be represented graphically by an arrow. Helps us think about a vector. So vector, so far we've actually been talking about vectors, whether you knew it or not. We have arrows that can be pointed to the right, they could have been pointed to the left. Those are forces, let's say. Or they could have been pointed up, or they could have been pointed down. So examples of vectors of quantities that could be vectors include forces, because they have a direction and a size, velocity, acceleration, and for that matter, position. It's actually a lot of things we've been talking about so far this semester. So that might lead you to ask, it begs the question, what isn't a vector? A vector is something that only has a size. An example of something that is not a vector would be speed or distance. Those are a couple that you can think of that aren't a vector. Mass, it's not a vector. I'm sure others will come to mind too. Time. All right, these are things that just have a size. They don't have an angle that we refer to in the direction of it. All right, so that is brief definition of what is a vector. Now the question is, why use vectors? And the reason is because so many things are vectors that by using the tools that I'm going to be teaching you, we'll be able to come up with ways of doing things that we couldn't have done otherwise. Let me give you an example. For instance, let's say I'll be doing a lot of problems involving walking because that's a great example of I'll think of a position vector. If I want to walk from here to here, let's say, and then I want to walk from here back down to here, I might ask you, how far from my initial starting point did I walk when going from here to here and from there to there? Now you might say, oh, if I just add up this distance, which I'll call R1, and that distance, which I'll call R2, add those up, then you'll get some other distance. The problem is that won't be this distance. That'll be a much bigger distance, actually. It would probably be somewhere out to here. So just simply adding them up isn't going to give us what R1 plus R2 is. And I'm going to illustrate that they're actually vectors by doing that. I also may want to know what's the angle that I have to walk to get to that final position. None of what we've talked about so far is going to be able to do that for us. So these are some reasons why I would want to use vectors. Now the first few examples I'm going to give you of vectors, you can actually see one of them here on this PowerPoint slide where I walk 4 kilometers east. Let's say I start at this side right here. That's my starting point. I walk 4 kilometers east, then I walk 3 kilometers south. Now the question I want to ask you is, how far from my starting point do I end up? In other words, if I was going to call a friend to meet me at the tip of this arrow, and because I forgot my lunch, because it's been quite a walk, and I'm hungry, I want my friend to take the fastest route possible to reach me. And I'm assuming this is a flat surface. So if that's true, then the fastest route is simply a line connecting that point and that point right there. Well, how far is that? And at what angle is that? And how do I describe the angle? So I'm going to do that, illustrate that problem here. And this will be an introduction to vectors, but it's very simple vectors. We're going to be able to do ones with more complicated angles than this shortly. but let's say I walk 4 kilometers at first and then 3 kilometers after that. Well, since I'm walking due east here, this is the direction. So you'll see me using east. North is usually the top of the page, west is to the left of the page, and south is down below from the point at which I start. In this case here, I'm walking 4 kilometers due east. And then from that point, I'm walking from this point here, south is directly below it. So from this point here, south is here. So then I walk 3 kilometers due south. The question is, how far do I walk from here to here? Well, since this is east and this is south, I know this is a right angle. And it's great when I can turn things into right angles, and that's a lot of what we'll be doing as we're adding vectors, is using right angles to help us deal with vectors. And in this case, it's the simple case because the two things I'm trying to add up are at right angles to each other. So the result is this line right here. Now my question to you is, how far is that line? And this is where we're going to use one of the equations that's incredibly useful in vectors, and that's the Pythagorean theorem. And you've seen it before, I'm sure. May have been a while. But it's telling me that I'll call this one R3, I'll call this one R1, and I'll call this one R2. It's telling me that R3 squared is equal to R1 squared plus R2 squared. All right, so that tells me that R3 is going to be equal to the square root of R1 squared plus R2 squared. So if I do the math here, R1 is 4 kilometers, so I take 4 squared plus 3 squared. That's going to give me the square root of 16 plus 9, which is going to give me the square root of 25, which is going to be 5 kilometers. That's how far R3 is. Great. Now my question is, what angle would I have to walk to get there? Now I'll be talking about how we describe these angles, but let's say I'm looking for this angle here. I'll have to describe how I name that angle, besides just the number of degrees it is. But first I want to be able to calculate the number of degrees that are in that angle. And there's 3 ways to do that I'll list right here. And this takes us back to trigonometry, and you might remember the acronym SOHCAHTOA, or the mnemonic device. That's telling me that it relates the sine of this angle here, the cosine of this angle here, and the tangent of this angle here. That's really all of trigonometry that you need to know for this class. But my experience has been a lot of students have forgotten SOHCAHTOA and or need a refresher on it. So I'm going to tell you what the relationships are for SOHCAHTOA. SOHCAHTOA, the first 3 letters tell me that the sine of that angle theta is equal to the opposite side divided by the hypotenuse. The opposite side here is 3 divided by the hypotenuse, which is 5. Hypotenuse is R3. That's the longest side of a right triangle. The second 3 letters tells me that the cosine of theta is equal to the adjacent side divided by the hypotenuse. I should say A over H, which is equal to 4/5. The tangent of theta tells me in general, that's the final 3 letters, that the opposite side divided by the adjacent side is what's equal to the tangent of theta. In this case, that's going to be equal to 3/4. All right? So let me find the angle theta. I could say, okay, I could use any of these 3 relationships, and it should give me the same angle of theta, and I encourage you to try it. If you take theta equals, the inverse sine of 3/5, put that in your calculator. You might also see it written as a sine or arc sine. It's another way to find the inverse sine. And you do that calculation, you should get 36.9 degrees, I believe. All right, so that would be true if you took the inverse cosine of 4/5. You should get the same result. Same thing for the inverse tangent of 3/4. You should get the same result. Okay, so that's how you find that angle theta. And then how do I express that angle theta? Because I could say, okay, that angle theta is 36.9 degrees. Since you see it on the drawing, that's good enough. What if I wanted to tell my friend what angle he had to walk to find me? Then I'd want to give him more specific directions. I'd want to say, okay, you're going to need to walk 5 kilometers. That's what I found here. And you're going to need to walk at an angle of 36.9 degrees south of east. I start looking east and I have to head south a certain angle from that. That angle is 36.9 degrees. So what I'll say is my final angle here is 36.9 degrees south of east. So I would tell my friend, walk 5 kilometers at an angle 36.9 degrees south of east. And we're going to be practicing. This is sometimes the hardest part, the south of east or the east of north or south of west, whatever it ends up being. I've experienced students have the hardest time interpreting that. So think about what this means, and we'll talk about it more. There's a few more videos on vectors that I'm going to encourage you to take a look at, which will talk about vector components. What is a vector component? How do I add things that aren't necessarily at right angles to each other? So there's 5 more videos on the site that you can look at. You can look at them before break, during break. They will be on the homework that you'll do that's going to be due after break. The first homework due is going to involve some vectors, as well as the Atwood machine and the hanging block problem. Okay, good luck with that.